Hey everybody, it's Dr. J. I'm up in the crib. So this is my house, or this is my home office within my home. And let's see, today we're going to talk about forces. Okay, so this is the first lesson in our units, a bunch of mini units on forces. And I've been trying to get this right because I want this lesson to be really, really fun for everybody. So let's go ahead and take a look at forces and get an idea of what they are. All right, so today we're discussing forces and we're going to have a spotlight on Newton's second law. And so let's get started just developing a sense of what a force is. So a simple definition of a force is a push or a pull, okay? And this is a qualitative definition. So that means no numbers, no calculation, right? Just purely descriptive, okay? So we can use words to provide a qualitative definition. Okay, words alone, no math is necessary. So a push or a pull. Okay, but what if you want a quantitative definition of force? Well, the first place to start with a quantitative definition of force is with Newton's second law. Okay, in Newton's second law, so Newton's second law states that force equals mass. So force equals mass times acceleration. Okay, so F equals ma. F equals m times a. And the standard units the standard unit for force, the base unit for force is N. That's actually newtons. And mass for this calculation is in kilograms, so lowercase kg. And acceleration is in meters per second squared, okay? So force in newtons equals kilograms times meters per second squared, all right? So that's a quantitative definition of force. And we're gonna make good use of that definition today. But first, let's go ahead and talk about a couple different types of forces. Okay, so the first type of force that we'll be discussing today is a contact force. Okay, and a contact force is just a physical push or pull and requires physical contact. So this isn't a complicated term at all. So one example would be pushing a shopping cart, right? So whenever you're pushing a shopping cart, you're exerting a force on the shopping cart. Okay, you're pushing it when you're in the store, right? So that's a contact force. All right, but what about a non-contact force? Okay. So a non-contact force that you could otherwise call a field force is a force that's exerted between objects that are not necessarily physically touching. Okay, so examples would be gravitational, magnetic, or electrostatic forces. And today, we're going to spend a lot of time thinking about gravitational forces, okay, and thinking about gravity. In fact, we're going to do a really fun little mini lab that I hope everybody will enjoy. So before we get there, let's go ahead and take a look at the way that gravity operates in the real world. All right, so gravity is a tricky thing. It's around us all the time. It's acting on us all the time, but we don't necessarily notice it, right? And we don't necessarily notice how strong it is. And these videos will show us just how powerful gravity is. So let's take a look at this first video. Right, so don't let this happen to you. That looks really, really rough, right? That looks really, really bad. And like this woman here, like I don't think I want her to be my friend, right? She seems to be having a really good time, right, with this dude, you know, in real trouble. There's that I don't know about her. Okay, I don't want to give her the wholesome award. All right, so here, right, gravity acting on a skateboarder. I've never owned one of these things. I think a man needs to know what will kill him, right? And for me, it's like motorcycles and water and probably skateboards. Yep, skateboards. Nope, I wouldn't see. This is not how I want to live my life right there, right? That's not it. That is not it. No need to watch that again. That's brutal. Okay. This is equally brutal, right? So, yep, nope. You don't want to be on that boat. In fact, neither do these guys. And off they go. That is a rough situation. Wow. Probably hundreds of thousands of dollars in equipment right there just like fell into the water. That's really tough. And then, again, right, like be careful with the whole like trust fall thing. I don't think I ever want to do this. Nope. I don't ever want to do this. I definitely don't want to do that. But like, I think in general, like, I don't want to try one of those like team building exercises with the falling, right? And then, if you're like installing a window, you want to make sure that your equipment is strong enough to lift the window. Otherwise, you could be liable not just for the window, but for anything below that gets crushed. So this is a rough situation. It's hard to imagine how this happens. Oof. Oh, yeah. Yeah. And these were like the videos that were like, like not so brutal that I felt like I could show them to you, right? Like you should see like, anyway, I won't give you any ideas, but but I found some videos like I was like, no, that looks too bad. I don't want to show that. Okay, so let's get back to talking about Newton's second law here. Okay, so we're going to get back to like talking very explicitly about forces and Newton's second law. So, okay, let me edit this. Oh, it's not letting me edit it with that. Okay, give me just a tick and I'll pull up the whiteboard on a different device. Okay, so again, today, we're really focusing on Newton's second law, which is also known as the F equals ma law. And what we're going to do today is we're going to make use of gravity and our own observations to learn about acceleration, force, and velocity, both academically, that is theoretically, and in practice in the real world. So in our own world. And so let's talk about how we're going to do that. Okay, so today we're going to perform a data collection and analysis. And when we say analysis, generally we mean calculations, okay, but not always. But today we will be doing some calculations. So let's talk about the purpose of the data we'll be collecting in our experiments today. Okay, so our purpose is to determine a golf ball's experienced gravitational acceleration, gravitational force, and velocity upon impact after being dropped from the second floor railing outside our classroom. Okay, so we've done this experiment before, but it's worth doing again. It's always a fun experiment to do, and it's always good to collect fresh data whenever we're doing a new data analysis, okay, or studying something new. So we're gonna go ahead and do this, and we'll talk about how we're going to interpret the results that we'll get. So let's kind of go through step by step what we're going to do here. Okay, so here's the first part of our procedure, step one. We're really breaking this into three different steps. Okay, so one, we're going to use the gram balance to find the mass of the golf ball in grams. Okay, the unit is G, grams. And we're gonna then multiply the gram mass by 1 kilogram per 1,000 grams to obtain the mass in kilograms. Because, as the note says, we want the kilogram mass so that we can use it for all subsequent, that means following, calculations. Okay, so go ahead and get this into your notes, and then we're going to head to step 2 of our procedure. Okay, and the second step of our procedure will be to find the average amount of time needed for the golf ball to reach the ground after being dropped from the railing. Okay, so average time in seconds, our unit is seconds, S, equals the sum of the 3 trials, all in seconds, of course, divided by 3. Okay, so that's our procedure here. Okay, we're gonna do our 3 replications just like always, and we're gonna add them all together, all of our times, and divide by 3. So this time we're gonna be calculating our average ourselves. Okay, we won't have a spreadsheet to do that for us. All right, so go ahead and get this step in your procedure, and then we'll head to step 3. Okay, so the next step is for us to determine the golf ball's acceleration, and we're going to use this handy formula. So A equals 2D divided by t squared. And if you're wondering where this formula comes from, right now I'm just giving it to you. When you get to Mr. Fosse's class, you'll so physics in 11th grade, you'll talk more about where this formula comes from. Okay, it turns out it comes from calculus. So really cool formula that you'll get to use later on in your science career and right now. So this formula is defined as follows. A stands for acceleration, and the acceleration is 2 times d, the distance that the golf ball drops to the ground, divided by t squared, where t is the average drop time. Okay, so A is the acceleration, D is the distance between the golf ball and the ground, okay, from the start of the experiment. And T is the amount of time that the golf ball needs to reach the ground, all right? And this distance to the ground, we know is equal to 4.9 meters, all right? We already know this. This average drop time you're going to calculate, okay? So go ahead and just leave that in your notes, and then we'll talk about our next calculation. Okay, so next we're going to determine the force that's acting on the golf ball. And we know from Newton's law that F equals ma. Okay, so what's going on here, right? So this is our force that we're trying to calculate. And the units that we're going to get are newtons. The mass, this is going to be the kilogram mass, okay, from earlier, all right? So we determined this kilogram mass earlier basically in step 1, okay? So earlier, so this is step 1 and 1A. Okay, so steps 1 and 1A. All right, so we've already determined this kilogram mass and this acceleration, right? We determined, and this is in meters per second squared. And we determined this acceleration, okay? This is from step 3, okay? The last calculation that we just performed, all right? So this acceleration we've just found, and the mass we found in step 1, and so then we'll be ready to calculate our force in newtons, okay? That's how we'll perform that calculation. All right, so lastly, we want to determine the golf ball's velocity upon impact with the ground. Okay, so how do we do this? So we have another equation that we're going to learn more about when we take 11th grade physics, but we can use it right now and we can understand it right now. So let's talk about it. So V subscript F, that means final velocity, velocity final, okay? That's the velocity with which the golf ball is going to impact the ground, and we're going to calculate that. So how do we do it? Well, the first term we need is the initial velocity, right? And actually, since we're just holding our golf ball, okay, this initial velocity equals 0 meters per second. Okay, so initial velocity equals 0. And then we have to add to that acceleration. That's from step 3. We've already calculated that, times time, which we determined in step 2 from our average. Okay, so it turns out that the final velocity for our experiment is going to equal just acceleration, which we've already determined, times time, which we've already determined. Okay, so this is going to be a pretty straightforward calculation. All right. So now we've talked about these calculations theoretically, and we have all the formulas and the steps to perform them in our notes. Let's go ahead and actually go through an example, just like the one you're about to perform, okay? So as usual, right, I've done this experiment myself, but I've changed it up a little bit. So instead of dropping a golf ball, I dropped the foam wiffle ball, sorry, not foam, but the plastic wiffle ball, the neon green one that sits on my desk in the classroom. So let's go ahead and take a look at that and talk about what I did. Okay, so here's my buddy, the wiffle ball, okay? And this guy, wiffle ball right there, okay? That sits on my desk. And here it is on the gram balance. And even though the gram, like finding a mass is step 2, let's just talk about that, okay? So we've got 70 grams, right? Plus 2. And if we look really closely, you can see this is kind of right in the middle, 2.55. So this guy is 72.55 grams, and you can see here that it's well balanced. Okay, and I'm just going to round that for my calculation purposes. I don't need to be more accurate than 2 significant figures. I'm going to round that to 73 grams. All right, so we'll use that number again when we find the mass in grams. All right, so that's my little wiffle ball, and we're going to go through steps 1 through 5 here so that you'll be really comfortable with these calculations before you collect your data. Okay, so here's our example. So I found the mass of a neon green wiffle ball, and timed its descent from the balcony to the ground. So what can we learn from this experiment? Well, the first thing we're going to discuss is acceleration. Okay, so we know that our formula is acceleration A equals 2 times the distance of the drop, all divided by the time squared, okay, the time of the drop squared. And from my experiments, so we already knew that the distance was 4.9 meters, but from my experiments, I found that the wiffle ball actually had an average drop time of 1.08 seconds. So plugging the numbers in, we have 2 times 4.9 meters divided by 1.8 seconds squared, okay, quantity squared, equals 8.4 meters per second squared. That's our acceleration, okay? This is our acceleration. So my little wiffle ball was accelerating at 8.4 meters per second squared, okay? So go ahead and get this example into your notes. It'll be very helpful as you perform your calculations, and then we'll look at the second calculation. All right, so the second thing we can learn from this experiment is the force acting on the wiffle ball, okay, or in your case, the golf ball. So how do we go ahead and find that force? What's going on? So we use our Newton's second law equation, F equals ma. And we know that our mass, okay, we got to find our mass. Our mass that I found on the balance was 73 grams. I multiply that by 1 kilogram per 1,000 grams. Grams cancel out, and I get my mass equals 0.073 kilograms, okay? And so force equals mass times acceleration. So mass here times the acceleration that we found in our previous calculation, okay? So this is m times a, right? And that's going to give us 0.61 newtons as our force. Okay, so the force that was acting on my wiffle ball was 0.61 newtons. All right, so let's go through that again. Really, all we're just doing is using F equals m times a. Okay, this is our equation. F equals mass times acceleration. This is our mass, okay, in kilograms. This is our acceleration from the previous calculation. We multiply the two together to get this force in newtons, all right? Very straightforward calculation. Okay, so let's take a look at the final thing that we're going to learn from this type of experiment today. All right, so the last thing that we can learn is impact velocity. With what velocity does this wiffle ball hit the ground? Okay, so the equation we want to use is velocity final equals velocity initial plus acceleration times time. But we have to remember that our initial velocity, since we're just holding the golf ball or the wiffle ball, we're just holding it there, is 0 meters per second. It's not moving. So that means that we can simplify this equation to the final velocity equals acceleration times time. Okay, so we've already found our acceleration and we've already found our time. Okay, so we have these values from previous calculations and or experiments, right? So velocity final equals acceleration, which we know, times time to give us our final velocity. So in my case, that's 8.4 meters per second squared times 1.08 seconds to give me 9.1 meters per second as my final velocity. Okay, so that's how fast that wiffle ball was going when it hit the ground. Okay, that's a pretty good sprint. 9.1 meters per second. That's like a pretty good sprint from a human runner. Okay. All right. So those are all of your calculations. Okay, that's how to go ahead and perform your lab. What you're going to turn in today is a series of photos of your notes, and you're going to come and talk to me about all of your results, and we're going to look at your calculations, and you're going to ask me questions and so forth. Okay, but turn in pictures of your notes and turn in pictures of your results and your calculations, and don't worry if you get something wrong. Okay, we're worrying about doing as much as we can today. These are new calculations. We'll spend a lot more time worrying about correctness next class, but we're still going to do our best, of course, to get everything right. And as always, okay, good luck. have fun, and may all the forces be with you.